Here is a question that arises in the formulation of a coherent system. Is there a distribution class that is closed under the formation of a coherent system? What is meant by closed in this case is that if each of the components falls in a particular distribution class, then for any system you can compose of components, will the lifetime of that system fall in the same distribution class? The answer to that question is yes, and that class is IFRA, which of course stands for increasing failure rate on the average. The component lifetimes and the system lifetime in the previous example that we looked at were both members of the IFRA class. So here is the definition of the distribution class IFRA. A failure time distribution is IFRA if the cumulative hazard function divided by t is a non-decreasing function of time. This is two definitions in one. It's also the definition of DFRA, which stands for decreasing failure rate on the average, if that ratio of the cumulative hazard function to time happens to be non-increasing. So here is a result concerning IFRA distributions, and this will give you an equivalent IFRA distribution. It goes as follows. A distribution is IFRA if S of alpha t is greater than or equal to S of t to the alpha power for some alpha chosen between 0, 1 and t greater than or equal to 0. Here is a proof of that result. For a distribution in the IFRA class, we know that the ratio of the cumulative hazard function to time is non-decreasing, and if we choose a t1 value that's less than or equal to t2, we know that capital H of t1 divided by t1 will be less than or equal to capital H of t2 divided by t2. Now, to simplify the notation a little bit, what you can do here is you can replace t2 with t, and you can replace t1 with alpha t, where alpha is chosen between 0 and 1, and this same result can be just expressed in this fashion. Capital H of alpha t divided by alpha t is less than or equal to H of t divided by t. Again, just replacing t1 by alpha t and replacing t2 by just t. When you go to the 5 by 5 matrix and you replace the cumulative hazard function by the opposite of the log of the survivor function, this term right here becomes minus log S of alpha t. And then when you let the t's cancel that are down in the denominator, which are here, and then you multiply through by alpha and also use the 5 by 5 matrix on the right-hand side, you wind up with that inequality right there. Finally, the last step, when you negate, both of these negatives will become positives, but the sense of the inequality will be reversed, so now we have a greater than or equal to. And then when you exponentiate both sides of the equation, you get e to the natural log of S of alpha t. That is just S of alpha t. And on this side, when you take this alpha right here and put it up into the exponent, and then take e to both sides, you wind up with S of t to the alpha. So we have just proven that this original definition here is equivalent to this right here. we'll be using that in a proof going forward. So here is the IFRA closure theorem. This is from page 85 of Barlow and Prochon's book. If the n components of a coherent system have IFRA distributions, then the system time to failure has an IFRA distribution. That is to say, the IFRA distribution class is closed under the formation of a coherent system. Now, this is an outline of the proof, not the complete proof, but it'll kind of give you an idea of the direction that the proof goes. First of all, the survivor function for the system lifetime is S of t is equal to R of S1 of t, S2 of t, up to Sn of t. That particular result is a combination of reliability functions, which were introduced in Chapter 2, and survivor functions, which were introduced in this chapter. And there is a separate section that looks at this particular relationship that we have gone over previously. Now, if this expression right here works for any t, then it's also got to work for alpha t. So all we're doing here is replacing t by alpha t, where alpha is some constant between 0 and 1. Next, since r is an increasing function, and why is it increasing? Because we have assumed that we have a coherent structure that we have put together. And furthermore, we are assuming that each one of the component lifetimes is in the IFRA class. This implies that Si of alpha t is greater than or equal to Si of t to the alpha for I equals 1 to n. And that is by the expression that we had on the previous page right here. Then, by the equivalent definition, so this is where the star indicates this is where you need another result to get to this last one. But then what we're going to do is we're going to have S of t, S of alpha t I should say, which is this quantity right here, the reliability function, to the alpha power. We know that S of alpha t is greater than or equal to that quantity. And furthermore, we know that the quantity right here is just S of t raised to the alpha. That is enough to tell us that the system lifetime t is in the IFRA class. So once again, to review in this case, when we have component lifetimes T1, T2 through Tn, and those component lifetimes are all in the IFRA class, then if you form any coherent system from those n components and look at the system lifetime t, then it will also be in the IFRA class. Here are 4 equivalent IFRA definitions. Here's the first one we looked at. H of t divided by t is increasing in t. That's how we did it first. And then the second thing we did was we proved a result that said S of alpha t is greater than or equal to S of t to the alpha for some alpha between 0 and 1. But there are other definitions. Here's one that you can just get with a one-step proof. If you replace the cumulative hazard by the opposite of the natural log of the survivor function, then you get this as an equivalent definition. And finally, if you take this 1 over t in this particular expression right here, bring it down in front of the logarithm, then what you could do is you could raise that to the 1 over t power, which is to say, if you negate and take e to both sides, S of t to the 1 over t will be decreasing now in t because you negated. So why do we study these IFRA distributions? Well, the first we just looked at, and that's the IFRA closure theorem. Second is, and this is also from Barlow and Prochon, any IFRA distribution can be expressed as the limit with respect to the number of components n of a coherent system of exponential components, and one more detail, also degenerate distributions may be also involved in this limit. So that's a second, and that's kind of a surprising result that says if you put enough exponential or degenerate components together, you can create any IFRA distribution. Finally, a third reason that IFRA distributions are of interest is shock models. And that says the time to failure of an item subject to shots occurring according to a Poisson process with cumulative irreversible damage is in the IFRA class. So before we look at shock models, couple precedence relationships. If you are in the IFRA class, then that implies you are also in the IFRA class. If you are in the DFR class, that implies that you are in the DFRA class. Okay, here's a little bit on shock models. The notion here is that an item accumulates damage from shocks until a threshold of damage is reached, and that's where the item fails. So for an example, an airplane without inspection or preventive maintenance, you've got to look at all the rivets that are holding the wing and everything else together periodically. And so that's an example of where a shock model would be appropriate. Another would be a suspension cable without inspection or preventive maintenance. So you can see the preventive maintenance and the inspection go about to slow down these shock models. Here are a couple non-examples. If you have an organism that undergoes healing, in other words, it can somehow get better, then you don't have the damage accumulating in that case, so you don't want to use it in that particular application. Another is if you have software that is self-correcting, then in a way the software is healing itself. Here are the assumptions. First of all, the shocks occur according to a Poisson process with rate lambda. Second assumption, the ith shock causes a random amount of damage x sub I. So the first shock causes damage x1, second shock damage x2, etc. x1, x2, etc. are IID. There is a way of relaxing this, but for now we're going to assume that they are independent, identically distributed. Finally, the item fails when the total damage exceeds some threshold x. We're going to draw a picture on this next page. On the vertical axis, you have damage, and on the horizontal axis, you have time. So we start out here at time 0, and somewhere along the way there is a shock. And let's say the first shock happens right here. And let's say x1 is the amount of damage from that first shock. So our cumulative damage is now up to here. And we may go a little while before we hit another shock, and that shock will be right here. And let's say that one causes more damage. That was kind of a heavy shock. So that takes you up to here. And then finally you go along, and maybe at this point right here, you have a third shock. It occurs right here on the time axis. Now that third shock, even though it doesn't cause that much damage x3, there is a threshold. And let's say the threshold for the amount of damage to cause failure is right here. If that's the case then, and by the way, we're calling this damage here x, if that's the case, then this third shock, that is the random time to failure t for this particular item. So the survivor function for a shock model is S of t is the probability that the item survives to time t. That's just our standard definition of a survivor function. That is the probability that the sum of the damages at time little t is less than or equal to x. Using conditioning, this can be found as follows. It will be the sum as k goes from 0 to infinity of the probability that there are exactly k shocks on the interval 0t and the probability that the total damage caused by those k shocks is less than or equal to x. That's the probability it will survive if the damage is less than or equal to our threshold x. Now, if we further assume that the shocks occur according to a Poisson process, then the number of shocks between time 0 and time t has this particular Poisson distribution right there. We have in this probability here a summation of random variables, sometimes called a convolution of random variables. Since we have that being less than or equal to x, that is the cumulative distribution of the sum of the shocks evaluated at x. So that is a general expression for the survivor function of the items. Once you fill in the distribution of these shocks, and they could be exponentially distributed, they could have the gamma distribution, they could have the log normal distribution. Once you fill those in, then you can calculate the survivor function using this expression right here. There are other classes of distributions that are out there. For example, one of those classes is known as the new better than used class. And a distribution is in the new better than used class if the survivor function at time t plus x is less than or equal to the survivor function of t multiplied by the survivor function at x. Now, most things that you purchase are going to be new better than used. If you went to a store and it had a brand new item and then you had one that was at home that was used, typically for most items you would prefer the new item because most items are wearing out. Now, for this particular model, you'll notice that if you divide through by s of x, this is written in this fashion. You will notice that the left-hand side of this is a conditional survivor function. Now, because it's a conditional survivor function, we can do a little bit of geometry in this case. So what we have is along that vertical axis, we have the survivor function. And here is 1, and here is 0. And let's say we have a survivor function that looks like this. That happens to be the left-hand side of the inequality, that thing right there. Then let's say that we have an item that has made it to time x. Well, if it has made it to time x, then it has a conditional survivor function, and we find that conditional survivor function by simply rescaling the right-hand tail of the survivor function. So there's the conditional survivor function, and that conditional survivor function is the right-hand side of this inequality. Now, what this inequality says is if you take this survivor function of the used item and you simply translate it to the left to where it is sitting, let's just say right here, when you translate it back to time 0, that is, you slide it, this will be the right-hand side. I have these backwards. Yeah, this will be the left-hand side and this will be the new item, so that's the right-hand side of the inequality. And what we have here is we are saying that the left-hand side of the inequality is falling below the right-hand side of the inequality, and that's the case for a new better than used item. There is, of course, the opposite distribution class. A distribution is in the new worse than used class if this less than or equal to in the inequality is replaced with a greater than or equal to. Finally, the last couple classes that we have, there is one called new better than used in expectation, and that is true if L of t is less than or equal to L of 0. So here is L of t to give you a little bit of the geometry. And you know for a mean residual life function that L of 0 is mu. So if we know that this right-hand side of the inequality is mu, this just says that L of t is less than or equal to mu. So if we draw a dashed line across here at L of 0, then all this says is that L of t must stay underneath that dashed line. Usually it's not a roller coaster like that, but I'm going to make a point when we go to the next class. There is also the opposite class, which is new worse than used in expectation, and that says instead of using a less than or equal to here, we use a greater than or equal to. Finally, the last two classes here, a distribution is in the DMRL, and that stands for decreasing mean residual life class, if L of t is a decreasing function of t. So if we draw that very same picture again, t along the horizontal axis, L of t on the vertical axis, we know once again that mu is L of 0. So we'll put a dashed line across there. And what this condition says, it says that L of t has to be a decreasing function of t. And by the way, whenever you see the word decreasing, a mathematician will bristle at that because it really means non-increasing. But in any case, it's a stronger property because this says we can't do any roller coaster. This thing just has to have a mean residual life that is monotonically decreasing. Of course, there is an increasing mean residual life class as well. If you go out in the literature and take a look, you will find that there are dozens of these classes out there. But the most important of the classes are IFR, DFR, and then IFRA, DFRA. Of course, none of these classes include things like a bathtub-shaped hazard function or an upside-down bathtub-shaped hazard function, and those arise as well. So this finishes Chapter 3, which is lifetime distribution representations. As we go to Chapter 4, we'll be looking at specific distributions, starting with the exponential and the Weibull.